Okay, let's start now. So, hello everyone, and welcome to the eighth lecture. This will be my lecture on statics. So, what is statics? Well, statics is actually pretty simple. It's just the study of problems where everything is completely still, so nothing is moving. And oops. Sometimes this actually makes stuff easier because we know that the net force has to be zero and the net torque has to be equal to zero. So this is kind of good. Like it gives us equations that we can use, and often times like these equations are useful, and also the configuration normally will stay the same, so that's another benefit to that. Okay, so there's an important point about choosing an origin, and this is mainly for problems that use torques. So, for example, let's say, I don't know, we have a balance beam, okay, and there's some person on the balance beam. Uh the point is, if we choose the origin to be like the pivot, it would be easier for us to solve the problem, because then we would we wouldn't have to worry about any of the forces that act at the pivot. So yeah, there's there's no one origin that you can choose, but you can like choose any origin you want and you'll still be able to solve the problem. However, like just choosing an origin that makes the problem easier for you, like choosing the right origin can make the problem way easier for you. So choose your origin wisely. Okay. Now let's talk about some common strategies when trying to solve problems. So first of all, this is like true in general, but you should always draw a diagram. And you should also draw like force diagrams, because those diagrams would be the most useful when you have to like think about uh the net force or the net torque that's acting on your object. Our second strategy is choose an origin. And after you draw the force diagram, you might have some idea of which origin to choose. And normally you would choose an origin that eliminates some annoying forces or forces you don't really want to deal with. If you choose an origin at the right point, you can make sure that the net torque from those forces is zero, and so you won't have to deal with those forces. Um, yeah, the next step is just to write down your equations, and then after that you can just solve them and you'll be done. So let's do a few examples. So I'll give you a few minutes to read this question and let you think about it. All right, it's been a few minutes, so let's get started. Um, so how do we approach this problem? Well, if we go back to our steps, the first step is to draw a diagram. So let's do that. Okay, we have our diagram. Um, but what's missing from this diagram? Oops. What is missing from the diagram? Yes, we need forces. Okay, so let's draw in some forces. Um, so now we have our forces. What's our next step? Yeah, we have to choose an origin. So what do we think? What do we think it would be a good origin for this problem? The pivot. Yeah, the pivot is the most obvious choice. It's also like the best choice because if you think about it, what forces do we know? So we know what the gravitational force is, it's just mg. And we don't really know what the tension force is yet, and we don't know what the pivot force is yet. But one thing that's really nice is that the angle of the string is given to us. So when we're trying to calculate torques, we'll know what the angle of the tension force is, but we won't know what the angle of the pivot force is. So when we're doing this question, it will be much easier to choose the pivot as our origin because that will make any force from the pivot contribute zero torque. So we don't have to worry about torque from the pivot. So we've chosen our origin now. What's our next step? Um, yes, so we need, remember our equations, right? What what equations can we use here? Well, since our setup is completely just at rest, we know that the net force has to be equal to zero, and also the net torque has to be equal to zero. So I'll give you a few more minutes to write down these equations and see if you can solve them. Okay, so let's think about this a little bit. Um, there's going to be so we've established there are three forces acting on the rod, right? There's gravity, there's tension, and force from the pivot. And gravity is just downwards. We know that the tension force is at an angle of theta, and the pivot force, we just don't know which direction it's going in. So let's split the pivot force into pivot X and pivot Y, and then we can write our F equals ma equations. So the equations are going to be here. And the first one is just the F equals ma equation in the X direction, the horizontal direction. So we can see that the tension force times cosine theta, that's the X component of the tension force. And there's also F pivot X, which is the the X component of the pivot force that we just defined there. Okay, now the second equation is the same thing, but in the Y direction. So we have Ft sine theta, which is the vertical component of the tension force. And we also add the vertical component of the pivot force. And we also have to subtract mg because that's the gravity force. And that should also equal to 0. And the last equation is the net torque equation. So this basically mg times L over 2, that's like force times distance for gravity. And that's just like the torque from gravity. And we have FL sine theta, that's also a tension force times the distance times sine of the angle. So that's the torque from the tension. And notice that they go in opposite directions. So that's why I put a minus sign there. And so when you add them up, that gives you the net torque, and that should also equal 0. So if you notice now, we know what theta is, we know what m is, we know what L is. So there's only three unknowns left. And these three are, of course, the tension force, the X component of the pivot force, and the Y component of the pivot force. Yeah, so we have three unknowns, and we also have three equations, which means we can solve these equations. So I'll give you another few minutes to solve these equations, and please, when you're done, please tell me what you get. Okay, it's been a while, so let's start talking about this again. So now all we have to do is solve these equations to get our answer, right? So how do we solve these equations? This should be just simple algebra, system of equations stuff. So we can start by solving the third equation. Maybe it'll be easier. So if we solve the third equation, we can immediately find the tension force. And after we plug that back into our first two equations, we can immediately solve the pivot force as well. And we can then find the pivot force in that way. So that's cool. And okay, so then that's basically our answer, right? Because if we go back to the problem asks us to find, the problem asks us to find the tension force and the pivot force. So from what we have, we know that we already know the tension force. So the tension force is equal to mg over 2 sine theta. And we can also find the pivot force, F pivot, which is the square root of F pivot x squared plus F pivot y squared, which also happens to be mg over 2 sine theta. Wait, is that? I'm not sure. No. Yeah, I think this is also mg over 2 sine theta after you simplify a little bit. And so these will be our answers. Okay, cool. Now let's go on to another problem. So I'll give you another few minutes to think about this problem. Uh, Remember to use the same strategies we talked about. This is a past F equals MA problem. And feel free to ask any questions or send me your answers once you have them. Okay. Uh, it's been quite a long time, so let's start talking about this question. So again, the first step is drawing a diagram. Well, we already have a diagram here, so that's done. Um, the diagram is missing something though. It's missing forces. So let's draw in the forces that are here. Um, there's going to be just four forces that we really care about, which are just the gravitational forces from each one of these masses. So that's that. Now, the second step is to choose an origin. So what do you think the origin should be? Mhm. Okay, so let's keep in mind there is also, oh, I guess I should be clear with what I'm considering our system here. So let's just take our system to be these two beams right here. So why do we want to consider these two beams and not anything else? Well, if you think about it, I guess okay, um there are other very good ways to do it. Let's just do it this way, which involves the torque. So if we think about these two beams, we can just basically consider it the same thing as one, I don't know, blobby object that has some forces acting on it, right? And for this object to be at rest, these forces and these torques have to all cancel out. So, first of all, what are these forces? Well, if we look at the mass M1 also has to be at rest. And if we draw a force diagram for M1, well, what do we get? We have gravity and we have tension. So M1 is at rest, so gravity must balance out tension. So the tension here must be the same as the gravity, which is M1G. And similarly here, there's M3G, there's M4G, and there's M2G right here. And there's also another force, which is force, I guess, the big tension force from the string holding the whole thing up. Okay, so now with this in mind, with this setup, what would be the best place to choose our origin? Anyone have ideas? On FT, yes, that is definitely the best place to choose our origin. And the reason why is FT, I guess with this problem, it doesn't really matter as much because FT is pretty easy to calculate. It's just the sum of all the downward forces. But in a more complicated problem, you normally can't immediately see what FT is. So if you just choose the origin to be right here, somewhere along this line, then well, the torque from FT is just zero. You don't have to worry about it. Um, so now we only have four torques to worry about, and we know what each of these are. So there's M1, there's the torque from M1, M1, G, and it's acting at a distance of 0.4 meters. Ooh, I should probably move some of this up. Oops. Um, how do I do this? Okay, anyways. We have the torque from M1, which will be M1 times G times the distance to the pivot, so 0.4 meters. There's the torque from M3. So M3 is 0.1 plus 0.1. That's 0.2 meters away. And then there's the torque from M4, which is 0.4 meters away, but it's on the other side, so that's negative. And there's also the torque from M2, which is 0.5 meters away. So the net torque here has to be equal to zero because otherwise it will start tilting, and that's not good. So we can just plug in the numbers. So up to some factor of 10, this will be, so we can just say 4, M1's 400, and times 0.4 meters, and M3 is what we want, and 0.2 meters. We have M4 is 500 times 0.4 meters, and M2 is 2 times 0.5 meters. So we'll get that M3 is, if we solve this, we'll get M3 should be 7, which corresponds to 700 grams, I guess, in our weird unit system. So that's our answer. Cool. There is also another sort of cool way to do this, which is to think about not the two beams as our system, but have the whole object be our system. This whole object here. And so if this whole object is our system, what are the forces acting on it? There's got to be gravity, and there's going to be some tension from the string that's holding it up. Okay, but we know that the system is in equilibrium. So, what can we say about this gravity and tension? Okay, yes, that's correct. So gravity and tension have to balance out. But there's something else that we can say about this. It's related to torques. Okay, so let's just say we have our box here. It's just chilling. What's the net torque on this box? Well, first we have to choose an origin. Um, it actually doesn't really matter. So there's gravity force, which acts at the center of mass, and there's tension force, which acts at the contact point. And in order for these the setup to not start tilting, the net torque has to be zero. The net torque has to be zero around any point. Um, so let's just choose an arbitrary point. We just established that the tension force and the gravity force have to be equal, right? But now let's think about the torques. So the forces are equal, but if they're different radii away from our origin point, that's not good, right? That means that the torques will be unequal and the whole thing will start spinning. So what this really just means is that they have to be the same on the same vertical line, because that way, that's the only way that the lever arms of these two forces will always be the same, right? If we just think about, or if we want to think about it in an easier way, if we just take the center of mass to be a reference point, gravity effectively acts on the center of mass. So there's no torque due to gravity there. And so there has to be no torque due to our tension force, which means that the tension force must also act on this line. So what does that mean for our problem? Well, that basically means that if we go over here, this line, our center of mass has to be on this line. So now we can just use our normal center of mass formula. So m1 times like negative 0.4 plus m2 times negative 0.2 plus m4 times 0.4 plus oops, this is in m3 plus m2 times 0.5 over the total mass, whatever, and this should be equal to 0. And we'll get the same equation that we just got. It's just a different way to do it. Okay, so now is 2:23, which is, I think we're at a good point in the lecture to stop for a break. So, let's call a short break. We will be back at 2:30 Pacific time. And I will also put the next problem on the board for you to think about if you happen to come back early. All right. Um, it is past 2:30 and I'm back. So now we have our third example problem on the board. It is also a past F equals MA problem. And I'll give you a few minutes to read it and think about it if you haven't already read it. Okay, so it's been a few minutes, so let's start thinking about this problem. So what was our first step to solve this problem? We have a diagram here, but what is the diagram missing? Yeah, it's missing our diagram is missing forces. That's kind of important. So let's draw them in here. So we have our sine right here. And an angle theta, a length L. L doesn't really matter. So can anyone tell me what forces are acting on this sine? Right. So the sine's going to obviously each leg of the sine is going to experience some gravity, and there also has to be normal force that holds it up. And there's also friction force right here. That's to keep it from slipping. There is another force here though. It's like the force from one leg on the other leg. And uh I think it can be um I think it has to be horizontal actually, but that doesn't really matter in this case. It's some force. It can be wherever. We don't know. So with that in mind, what should our origin be? What's the best choice of origin here? The hinge, exactly. Because we have no idea what these forces are. Whatever is going on, if we choose our origin here, we don't really care. So now let's just look at one leg of this sine object. So here's one leg. Here's the hinge, that's our origin. And there's going to be gravity. There's going to be normal force. And there's going to be friction force. So do we know what gravity is? Yes, we should know what gravity is. It's just mg, where m is the mass of one leg. So not the entire thing, it's just one leg. Okay, do we know what normal force is? Hmm. Now this one's a bit trickier because I did say there can be whatever forces acting at the hinge. But it turns out, yes, it's just opposite the force of gravity. And why is this? Well, if you look at the whole sign as a whole, the whole gravity force, the total gravity force will be 2 mg because there are two legs. And the total normal force must also be 2 mg. And because of symmetry, we can just assume that it's just mg on each leg. So the normal force here should be equal to mg. Okay, so now can we find friction? Yes, we should be able to find friction. So um let me just copy that diagram down here. And I'll give you a few more minutes to do the calculations and tell me what the force of friction is. So also it will be easy. You'll probably need that this angle over here is theta over 2. That's just simple geometry. So we want to find friction in terms of mg and theta. Because we know that friction is just mu times the normal force. Friction is mu mg, right? So if we can find friction in terms of mg and theta, then we can just set these two to be equal to each other, and then we'll be able to solve for theta. So I'll give you a few more minutes to think about this and do your calculations. Okay, so let's continue. So I hope you guys should have found friction by now. If not, I'll just quickly do it right here. To find friction, all we have to do is set net torque to be equal to 0. Oops. So the net torque should be equal to 0. And so there are three torques, of course. There is the one from the normal force, so that will be just mg times L times sine of theta over 2. And there's torque from gravity, which would be in the opposite direction, and mg, and this time it's only a distance L over 2, and the angle is also theta over 2. And finally, there's torque from friction, which is also in the other direction. There's going to be the torque from friction will be equal to, there's the frictional force times the distance, and this time cosine theta over 2, because the angle is like 90 degrees away from theta over 2, so we have to cosine instead of sine. And this whole thing should be equal to 0, of course. So now we can just solve it. If we move friction to the other side, we'll get mg L over 2 sine theta over 2 equals friction times L times cosine theta over 2. Okay. And now we can just simply solve this. L's go away, and friction is mg over 2 tangent theta over 2. Okay, but remember that friction is mu mg. So this is equal to mg over 2 tan theta over 2. So what this means is that theta has to be such that tan theta over 2 equals 2 mu. And so I believe that's our answer. Okay, any questions? If not, I will go on to the next problem. Okay, then let's go on to our fourth question. This one's a bit easier. I'll give you a few minutes to read the question. Remember to draw a diagram, and yeah, send me your answers once you have them. Okay. Um, it has been a few minutes, so let's really quickly just draw a diagram. Um, so we have a beam and we have a person here, and it's supported by two supports. Okay. The balance beam has mass big M, and the person has mass little m. Okay, and this length is L, and this length is X. Oop, it's a bit too high. Okay, so we want to find this normal force and this normal force. Let's call it N1 and N2. So, what equations can we write here? Any ideas? So, there are two unknowns, which means we'll need two equations, right? Well, we can get two equations from force balance and torque balance. So let's write down force balance first. That shouldn't be too hard. And what that says is the net force on our system must be zero. So let's just take the person and the beam together to be our system. And the net force on that will be just Fn1 plus Fn2 minus mg minus mg. And this has to be equal to 0. Okay. And now it's time to do torque balance. Now, what do you think would be a good pivot point to do torque balance around? The person, okay, so the person is definitely a good pivot point. Sure, let's try the person. Okay, so the torque around the person, there's going to be Fn1 times X. That's the normal force. And then there's the gravity on the person. That's 0 because the person is our pivot. Then we have mg. It's in the other direction. No, it's not in the other direction, actually. And what's the distance? Well, the distance should just be L over 2 minus X. And finally, the right pivot, this one's actually in the other direction, and the distance is L minus X. So yeah, we can like solve this. this is equal to 0. We'll get a system of two equations and we can solve it. But actually, I chose this problem because it illustrates an interesting point, which is we don't even need to keep our pivot the same. We can choose two different pivots if we want to, and that'll give us two equations, which will then like make force balance actually unnecessary. So one interesting method that I have seen is to first choose the left endpoint as the pivot. So what's the torque around the left endpoint? Well, there's the person, so that's mg times x. And then there's the mass of the balance beam. So that's mg times L over 2. And then there's the mass, there's the force from the other support, which is in the other direction, and it's Fn2 times L. And this is equal to 0. And the benefit of doing it this way is that we can immediately solve for Fn2, right? It's just mgx plus half mgx L over L. Okay. And similarly, if we choose the right endpoint to be our pivot, well, now what's the torque? There's the torque from the person, mg times L minus x. There's the torque from the balance beam, mgl over 2. And there's the torque from the first support now, Fn1 times L. And we can immediately solve for the force from the first support. So that will be Fn1, and it's equal to mg L minus x, 1/2 mgl over L. And we could have even just noticed that the whole setup was symmetric and just use the first equation, because the force from the first one is basically the same formula as the force from the second one, but now instead of a distance x, it's just the distance L minus x. So we just replace the x with an L minus x, and we get the same thing. So yes, this is a cool way of doing it. And it is quite a bit easier. All right. So now we have some time left. We have 30 minutes left, and we have one more problem that I have prepared. But this is quite a complicated problem. So bear with me with this one. This is an example from Morin's book. And in the book, there is a diagram. So I'll draw a diagram for you here. What we have is a stick that rests on a cylinder. So it will be much easier once I draw the diagram. So what we have here is, first of all, there are two walls. So one wall here and one wall here. And there's a stick that is right here. So the stick goes at a 45-degree angle, right? Starts here, this is 45 degrees. And it keeps on going until it reaches this wall. But it doesn't actually touch the wall. There's like an infinitely small gap between the stick and the wall. So this doesn't touch. So then you might ask, well, what's holding the stick up? Well, it turns out there is a cylinder here. The cylinder touches the left wall, and the cylinder also touches the stick, and it goes down, and it almost touches the ground, but it doesn't actually touch the ground. So it's infinitely close to touching the ground. Doesn't touch. So this is quite a weird setup, but it turns out that if there is enough friction, this setup can still stay stable. So if there's enough friction, the setup can be stable. It's a bit counterintuitive, but it is true. So the question is, assuming that this surface has a ton of friction, so cylinder and wall, there's a lot of friction, a lot of friction. Now, what is the minimum friction here? So that the whole setup stays stable. Yes. It's sort of a counterintuitive balancing act. Turns out though, you can do this according to the problem. Turns out you can also calculate the friction needed on this wall between the wall and the cylinder. But yeah, the problem asks for the stick and the cylinder. So we don't have very much time left for such a complicated problem. So I will just switch to here and start explaining maybe. So hopefully we don't need the problem statement anymore. And so let's start out with like an actual diagram. So we want forces. So there's our cylinder and there's our stick. And this is a bit more complicated also because it needs forces on two different objects. So, which object do we want to do first? Let's just do the stick first because why not? So what are the forces that are acting on the stick? Yes, that is correct. So on the stick here, there's going to be gravity, and there's going to be normal force, and there's going to be some weird force from the ground, which we don't really know. So I think it's pretty clear what we're going to want to make the pivot the origin. Yes, this should be our origin. Oh, wait. Sorry, there is one more force on the stick. Can anyone figure out what the other force is on the stick? Yes, it is friction. So there's friction here, but it turns out we don't really need to care about friction in this case because friction points towards the pivot. So there's no torque from friction. Okay, cool. So now let's use net torque equals 0 on the stick. So how will we do that? Well, oh yeah, one thing I forgot to mention is the cylinder has mass m and the stick also has mass m. So they have the same mass. Okay, so now the torque from gravity. First of all, what's the torque from gravity? Yeah, so it's going to be the gravitational force. So first of all, that's mg. And then the distance, we have to multiply by the distance. The distance isn't given to us, but that doesn't really matter. Let's just call it L. And then we have to multiply by the sine of the angle, so √2/2. Okay, and now what's the torque from the normal force? Yes, that is correct. It's the normal force times L, and it's in the other direction, so negative there. All right, and this is equal to 0. So immediately, we can solve for our normal force. It must be mg times √2, mg times √2/2. So that's very cool, but there is a second object that we have to worry about, which is the cylinder now. So what about the cylinder? Let's just replicate our diagram here. Circles are hard. So remember the cylinder is touching this wall. It's not actually touching the floor, and it's also touching the stick. So what forces act on the cylinder? Well, there's gravity, that's correct. There's gravity, that's mg. There's friction from the wall, that is also correct. And which direction does friction from the wall point? Well, intuitively, it has to point upwards because otherwise there wouldn't be much that's supporting the cylinder from falling down. So there's going to be friction here from the wall. Okay, and there's also here friction from the stick. Okay, there are more forces that we did forget though. There's two more forces that we should add to this diagram. Does anyone know what they are? Okay, so the forces that we need to add are the two normal forces. So there is going to be normal force from the wall, and also there has to be normal force from the stick. How do we know that? Well, the stick felt normal force from the cylinder. So by Newton's third law, there has to be an equal and opposite force on the cylinder from the stick. Okay, so I think that is all the forces that we need for this part. So how will we approach this? Remember what our third step, so our steps, like we've drawn a diagram, find a pivot. That is our second step. So, um, sure. I guess this step kind of goes with the third step. What I was getting at is we have to write down our net force and net torque equations and find a pivot, of course. So what should our pivot be here? Any suggestions? Hmm. Okay, this is a bit of a tricky one. I would say definitely the center of the cylinder is the best pivot to do your torque equations around. This is, I guess it's kind of intuitive because if you think about it, the both of the normal forces, so if you have a cylinder, right, any type of normal force has to be pointed towards the center, right? Any normal force possible is always pointed towards the center of the cylinder. So if it's pointed towards the center, that means that there's no torque. So we can basically ignore all of that. And also gravity, right? Gravity acts on the center, so that also goes away, and we're left with two forces. So these are the two friction forces. And we can very easily see now that, yeah, all the friction forces are the same distance from the center. So if we want to balance torques, we'll get that these two friction forces are equal. So they're equal. Okay, so that's cool. Um, but we still have two unknowns, right? So we know what M is, we know M. We know what this normal force is. That's just the mg root 2 over 2 we calculated earlier. But we don't know what the friction force is, and we don't know what the second normal force is. So we need to write more equations. We need two more equations. And luckily, we do indeed have two more equations. Do you know what they should be? Yeah, so we can split stuff into X and Y components. And then what we'll just do is say net force in each direction should be equal to 0. So let's do the horizontal direction first. So um F net in the X direction should be equal to 0. So which one of our forces are in the X direction? This first friction force here, that's completely vertical. this normal force here, that's completely horizontal. So yes, there's Fn2 here. Gravity, completely vertical. And the normal force and the second friction force also both have their horizontal components. So, oops. Yeah, so we'll have to, they're also both going in the other direction. So yes, minus root 2 over 2 times the friction force minus root 2 over 2 times our normal force, which was mg root 2 over 2. And this is equal to 0. So I think this will simplify down to Fn2 minus root 2 over 2 Ff equals 1/2 mg. Yep. Okay, now let's do the y direction. F net, oops, in the y direction equals to 0. So same thing here. We have our first friction force, which is now upwards. So we want that. There's gravity, which is downwards. And then there is our second friction force, which is 45 degrees upwards. So we have to multiply by root 2 over 2. And our normal force, which is downwards and at a 45-degree angle. So we have this. Okay, interesting. So yeah, this is, so after you simplify this, I believe you will get not normal force, but friction force times 1 plus root 2 over 2. And on the right-hand side, you should get 3/2 mg. Okay, so that's pretty nice because from this second equation, we can immediately solve for friction force. Friction force is 3 mg over 2 plus root 2. Yeah, I think that's what it is. And I think this will also simplify. Yeah, I think we'll want to simplify this to make it easier. So 6 minus 3 root 2 over 2. That's just rationalizing the denominator. And now we can plug this all the way into our first equation. We have that Fn2 is 1/2 mg plus root 2 over 2 Ff. And if we plug it in, 1/2 mg, and then root 2 over 2 friction is mg times 3 root 2 minus 3. Interesting. So I think this is just mg 3 root 2 minus 2. And now the coefficient of friction we want is just F friction over Fn2, which is mg 6 minus 3 root 2 over 2 over, it's divided by mg times 3 root, oops, 3 root 2 minus 2 over 2. And let me just pull out a calculator to make sure I don't make any mistakes. Uh-oh. It appears that I have made a calculation mistake somewhere. Um, that is weird. Oh, wait, never mind. Okay, no calculation mistake. So, yeah, that's kind of my bad. So this right here is actually the coefficient of friction between the cylinder and the wall. But what the question asked for was actually the cylinder and the stick. So that's a bit easier actually. The mu that we actually want is the friction force divided by Fn, not Fn2. So this becomes uh 3 mg over 2 plus root 2, and then Fn is just mg root 2 over 2. And if you do some quick maths, this simplifies just to 3 root 2 minus 3. And so that's our answer. Cool. Yeah. So there is a different normal force, and that's why the coefficients will be different. Cool. So I guess we are done a bit early, and let's switch back to our scene. We So thank you for listening. If you have any questions, you can ask me now. We actually have time for questions this time. And yeah, other than that, thank you for listening and see you next time.